So in the previous couple of lectures, I told you about the theory of Newton's method and how we apply this in function spaces. So let's say to solve nonlinear partial differential equations. And what I would like to do in this lecture is that I show you how it's actually implemented in practice. So there's a tutorial program, it's called Step 15, that implements this, and I would like to walk you through this and maybe have a few considerations that we have to think about when we implement a program like this at the beginning of this lecture. In the following lectures then, I will show you alternative methods how you can implement solving the minimal surface equation. That's the example that Step 15 solves. So I'm going to show you in the following lectures how to do this with other methods to solve nonlinear problems that are not the Newton's method. So this is lecture 31.6, nonlinear problems and Newton's method. So just to recap, we want to solve the minimal surface equation, which is written like this, so minus divergence, and there's a coefficient a over square root of 1 plus grad u squared times the gradient of u equals f, and then we certainly have boundary conditions. For step 15, what we choose is that the domain is the unit ball, so it's the disk of size 1 centered at the origin. Then for simplicity, we're going to use 0 right-hand side, and as boundary values, we're going to choose sine of 2 pi times x plus y. Our goal, as I said before, is solve this equation with Newton's method. And we've walked through this in the last few lectures already, so if you want to solve this particular problem with Newton's method, what you need to do is you need to solve a problem where I'm going to solve for delta UK in every step. So delta UK appears in this term and in this term. And on the right-hand side is the residual of the equation. This is the weak form of it. We've derived it in the previous lecture. If you discretize it, then you replace the delta UK by a sum over j times shape functions phi j times coefficients delta UK j. And so, of course, what you get here is sum over j of some matrix aij delta uk j, and on the right-hand side, these are my fi's. Okay, and then when I compute this delta uk, then I compute the update uk plus 1 equals uk plus delta uk. So in matrix form, what I need to solve is ak delta uk equals fk, and then when I have delta uk, I can compute the update. And down here, you see the form of the matrix in the first row and the form of the right-hand side down here. So this is the sort of thing that I need to assemble in every Newton iteration and then solve the corresponding linear equation that I have up here. Okay, so when you lay out this program that this is what I need to solve, then we need to ask a few questions. Namely, if I have this linear system and this is my matrix AK, this thing here, so it depends on gradient of UK, of the gradient of the previous Newton iterate. What is the appropriate solver for this linear system? Now, if you look at this carefully enough, you will find that indeed it is a symmetric and positive definite matrix, and as a consequence, this is appropriate to solve with the conjugate gradient method. If you go to step 15 in the introduction, we give a discussion of why this matrix really is symmetric and positive definite, so there's more information there. Intuitively, the reason why it is symmetric is because the matrix A is the derivative of the operator, and the operator is the derivative of the energy functional. If you go back a couple of lectures, you will remember how we derived the minimal surface equation. It was always that we tried to minimize a certain energy functional. So the operator was the derivative of the energy. This A, the operator that gives rise to this matrix here is the derivative of the operator of the nonlinear operator. So A corresponds to a second derivative, and the matrix of second derivatives, of course, is symmetric because we can exchange the ith and the jth derivative. The matrix is also positive definite because we try to minimize a convex energy functional. And if we try to find the minimum, clearly the energy must be convex, so the energy functional curves up, and the matrix is something like the matrix of curvatures in all of the directions, and it needs to be positive. Otherwise, we would not be able to find a minimum, but let's say only something like a saddle point, or maybe a maximum of the energy, and that's not what we want. Consideration 2. So when I want to solve for delta UK, what should be the boundary values of delta UK? And that goes back to very similar considerations as we had in lecture 21.5 about boundary values. So here, what I want to do is, let's say I choose my initial iteration u0 already in such a way that it satisfies the correct boundary value. So u0 on the boundary is equals to g. I certainly want that u1 is also equals to g on the boundary. And u2 in all of the following iterates should have the correct boundary values. So I have that u0 equals to g, and I want that uk plus alpha k, that's the step length, we're going to talk about this, so uk plus delta uk should also be equals to g on the boundary. Well, if uk is already g on the boundary, then delta uk must have 0 boundary values. Otherwise, I would compute the wrong boundary values for uk plus delta uk. Okay, so delta uk must have 0 boundary values. Okay, more considerations. So if you write down Newton's method in the original form, uk plus 1 equals uk plus delta uk, then you remember from your basic numerical analysis courses or numerical methods courses that this iteration might sometimes converge and sometimes it doesn't. In particular, if you start too far away from the exact solution, then it may not converge. Newton's method has a radius of convergence that is proportional to something like the second derivatives of the function divided by the third derivatives divided by the second derivatives. So if you have a strongly nonlinear problem with large third derivatives, then you end up with something that, I gave you the wrong definition, it's something like the second divided by the third derivative. So if you have something with a large third derivative, a strongly nonlinear problem, then you end up with something with a very small radius of convergence. So you, if you start from too far away, then your iterates will just wander off into somewhere. They might converge to something that is not a solution, or they might not converge at all and diverge to infinity, or they will cycle and will go back and forth, or take loops around the place that you want to converge to. You have to start close enough to the solution. Now, if you don't know a point close enough to the solution, then you can't start there, right? I don't have the exact solution. I don't know what to do if this is my initial guess. If this is outside the radius of convergence, what am I going to do? So one of the solutions that we often employ is that we say, well, instead of taking a full step, we're going to take a partial step. So the Newton iteration, so I know uk, it computes the delta uk, and instead of computing uk plus delta uk, I'm going to take a step length. So in formulas, this looks like this, that I have uk plus 1 equals uk plus alpha k delta uk, and alpha k is a step length that we will choose less than 1, between 0 and 1. Okay. The algorithm for determining what this alpha k should be is typically called line search. And there are multiple approaches to this. So maybe to give you a little bit of an let's say feel for what that alpha k should be. So ideally, of course, we would want to choose alpha k equals 1 if we can, if we know that it converges. If we can't choose alpha k equals 1, then we know that Newton's method converges very rapidly, namely quadratically. It does not converge with quadratic rate, but for example only with linear rate or superlinear if this alpha k is chosen to be less than 1. But at the same time, we may not be able to choose alpha k equals 1, and in that case we have to choose alpha k less than 1 until such a point as we are close enough to the solution that we can choose alpha equals 1. Okay? So the approach that we choose, or that we usually take when we want to compute what this alpha k should be, is we define ourselves something that is called a residuum. Okay. So if I give you a solution, then I can compute the residual of u, which is Lu minus f, okay, and it should be equal to 0. Now, if I give you any intermediate iterate uk, for example, of course it will not be equal to 0, but r of u will give us an indication of how close we are to the exact solution. So what we're going to do is we're going to try out a step length alpha k equals 1, and we're going to compute r of uk plus 1 times delta uk. So that's like the full step Newton iterate. Okay. And we're going to ask, what is the residual for this full step? And if it is less than some reduction factor times the residual of where we currently are, then we're going to accept this alpha. But if this alpha is too large, then what sometimes happens is that the residual of uk plus alpha delta uk is not, in fact, better than what we had before, but it becomes larger. And in that case, we reduce alpha k. So we choose, let's say, we try again with half the alpha k, or 2/3, or I mean something that is smaller than what we just had, and we try again whether the residual is smaller than it was before. And you can show that this almost always converges. For one alpha k small enough, there will always be some alpha k that satisfies this condition. And then that's the one that we're going to choose in our Newton iteration. So we're going to choose uk plus alpha k delta uk for the first alpha in this ever decreasing sequence of alpha k that satisfies this condition here. In practice, there are other criteria. So we let's say if you go to the theory of optimization, you will find that there are other criteria that we have to satisfy for this to be a valid step length alpha k. So they're called Wolfe condition or Armijo-Goldstein conditions. I'm not going to go into too many details here. There's a whole theory about what works and what does not work. And the other thing that I should talk about, or at least mention, is that we need to define what norm we actually mean. You remember that r of uk was the operator applied to uk minus f. So this thing here is lives in function spaces. For the case of the minimal surface equation, for example, it is an element of h minus 1, because I have a function in h1 and I apply second derivatives to it, so I get something that is in h minus 1. And it's a good question, certainly, what kind of norm we want to choose. So in the program, we have a function that measures this here in the dual norm of the discrete space. So I'm just going to multiply r of uk with test functions and integrate over the domain, and then I'm going to take the little L2 norm of the vector that I get when I multiply this with all of the test functions. That may or may not be the appropriate choice, but it's the easiest way to compute it for sure. Okay, now that's sort of the theory. In step 15, what we do is we, for simplicity, always choose alpha k equals 0.1. That's not the optimal choice to choose, but it is the simplest choice, and there's a longer discussion in the results section that talks about how to actually implement a line search. Okay, the last thing that I would like to mention here is that in step 15, we would like to solve on a sequence of finer and finer meshes. So the outline of the algorithm that we're going to use is that we start with a coarse mesh, then on the given mesh, we do 5 Newton iterations. We ask if whether at the end of this, or let's say we stop this whole process if the residual has become less than a tolerance, which I'm going to choose as 10 to the minus 3, but that's arbitrary. I could have chosen something else. Then we're going to save the solution on the current mesh and refine the mesh, and then restore the solution on the next mesh, because we want to, on every mesh, we don't want to start from scratch, but we want to start, of course, with the best possible iterate we had from the previous mesh. And if we haven't converged yet, then we'll just go back to step number 2 and do 5 Newton iterations. The number of 5 is completely arbitrary here. What we should really be doing is to have on every mesh a stopping criterion on how many Newton iterations we want to do. And what you will typically find, for example, is that let's say, on the first mesh, you have to do a fair share of Newton iterations, but then on further meshes, because we start from the previous interpolated solution, or let's say from the solution of the previous mesh interpolated onto the current one, the following meshes will only require 1 or 2 or at most 3 Newton iterations to converge. So there is certainly room for improvement in that program, but that's not so much the point. So with this all said, let's just look at the actual implementation of this equation in the code. So I already have this open here. Let me see if I can make the text a little bit bigger. So maybe before I show you the code, I'm going to show you the output. So I told you that we solve on a circle. Okay, the boundary values are a sign that goes up and down. Okay, and well, so what you see here is we start on the coarsest possible mesh. Okay, that's just a couple of times refined the disk, and then as we progress, we become more and more refined. The final mesh looks like this, so might be hard to see, but you see how it's refined here at the edges. Okay. Okay, so to show you the program, it's a program that was written by a student in a course that I taught when Wetter Hour. So it borrows heavily from step 6. So if you look at the main class, minimal surface problem, it basically looks like step 6 with just a couple additions. So there's a function set boundary values that I'm going to explain to you in a second. What it does, there's a function that's called compute residual and determine step lengths. Determine step length simply returns 0.1. But that's subject to improvement. And then compute residual, that's the function that we're going to use for the determination whether our iteration has converged. And we're also going to use that to create output on the screen to give us let's say, an indication of progress. The member functions look basically like we had in step 6, with the only addition that we have to have a variable that keeps track of the current solution, so that's my UK, and the Newton update, that is going to be the delta UK. Okay. So then, as we always do, we go to the bottom of this program. We look at main. So main just creates an instance of this problem and then calls run. So the next step that I need to look at is run. So what we do in run is we first create a mesh. Okay, there's nothing magic about it. And then we have this this loop here that we terminate if the residual is less than 10 to the minus 3. Okay, so while the residual is larger than 10 to the minus 3, or we are in the very first step, we're going to iterate. And what we do here is, let's say, in the very first step, we set up the system and we set boundary values. So set boundary values is a function that is actually quite trivial. What it does is it just interpolates the boundary values from the exact boundary values. That's a class that I define up here. Let's see, where did it go? No. Here, boundary values, okay. That just returns sine of 2 pi x plus y. That is the class that defines the boundary values that we want to apply to the problem. So in this function set boundary values, we interpolate the boundary values into this map here, okay, from index to corresponding value. And then we're going to iterate over the elements of the map, and we're going to set in the present solution, p arrow first gives me the index of a boundary degree of freedom, and we're going to set it to the corresponding value. Okay, so after I call this function, the variable present solution that stores the UK has the correct boundary values. Okay, it may be incorrect in the interior, but at least it has the correct boundary values. So going back to run, so I set up the system and I make sure that my U0 has the correct boundary values. Okay, and then I'm going to do my 5 Newton iterations here. Okay, and each Newton iteration is just a sample system. Okay, I'm going to store the residual, that's my stopping criterion. That's just the norm of the right-hand side, because the residual is the right-hand side of the Newton iteration. And then I'm going to solve. Okay, and at the end of each iteration, I'm going to compute the residual with a step length of 0. So that gives me the residual of uk plus 0 times delta uk. Okay, and that's it. So then the only thing that I really need to add is that at the end of the 5 iterations, I'm going to create output, as I always do, that I can visualize. So let's go through the other functions that I have here. So there is, of course, my setup system function, which is pretty trivial. So it takes an argument initial step, whether this is the first time we call this function. If it is the first time, then I'm going to distribute the UFs, reset the present solution. That's something, of course, that I don't want to do if it's not the first iteration. Okay, I compute hanging node constraints. I reset the Newton update and the right-hand side, and so on and so forth. Nothing special here. In assemble system, if you go back to the slides, you will find the matrix that I need to assemble. I can go back there as well. So the matrix that I need to assemble looks like this. Okay, so it is like the gradient, the Laplace problem times this coefficient, and minus some other term that involves phi j here, and this should be a phi I, but then the old solution uk here, and uk, this should be a ukh here. Okay, so I have here this a I'm going to set to 1, so I have 1 over the square root to the 3/2, and here 1 over to the square root. So I'm going to define a coefficient that is 1 over the square root, and here it's just 1 over this coefficient, or this coefficient cubed. So if you go to the code, I'm going to define the coefficient, which is 1 over the square root, and what I need is the old solution gradients at the current quadrature point, and I get that by calling fa_values.getFunctionGradients. Okay, the input argument of this is the current solution, that's my uk. So that's the vector of all nodal values, and what getFunctionGradients returns is a vector of gradients at the individual quadrature points. Okay, so that's defined that here. So it is a vector of tensors, because the gradients are tensors, old solution gradients, and these are the quadrature points, the NQ points, quadrature points on the current cell. So I get this here. I have my loop over all of the quadrature points. I compute the coefficient at this quadrature point. Then I'm going to have my loop over I and j, and I have here gradient phi I times the coefficient gradient phi j minus gradient phi I times the coefficient, that's the 1 over square root to the 3, okay, times the gradient phi j times the gradient of the solution itself at a quadrature point times this thing again. Okay, so if you go back to the formula, that's what I need to compute, and the right-hand side is just the residual of my equation. And the rest of it is totally standard. Then I apply hanging node constraints, and I interpolate 0 boundary values, because the update delta uk has to have 0 boundary values. Okay. So once that is computed, I just have to solve it. So that works as I always do. So I use CG and an SSOR preconditioner. After that, I apply the hanging node constraints to the solution. So I make sure that the midpoints, so let's say the hanging nodes themselves, are 1/2 of the neighboring values. And then I update my solution, present solution, add alpha times the update. Alpha is determined by this determined step length function, which here simply returns 0.1. So the only thing that is of a little bit of interest that's left is this refine mesh function. because that has to transfer data from the previous mesh to the current mesh. And that's a process that may be a little bit too complicated to explain right here. But if you go to the description of the tutorial program, you will find how that actually works. So with this said, I will show you just real quick what happens when I run this program. So let me go to example step 15. Okay, I'm going to say cmake dot. I'm going to say make. And then make run when this is done. Okay, the computer is taking its time today. Okay, so make run. Okay, so what you see is it converges. Okay, so in every on every mesh, the residual decreases. What you see is it does not decrease particularly fast. That is a consequence of the fact that we use alpha equals 1. So one of the things that would certainly help is if we could start from a point close to the solution, and we would use something that has a value of alpha closer to 1 or maybe equals to 1. What you will find in a case like this is that it converges very rapidly. So quadratic convergence means that the number of correct digits doubles every time, or that the number of zeros at the front doubles in every iteration. Basically, that's the statement. And so in a case like this, we would converge very rapidly towards the solution. That requires a little bit of playing with this alpha here. So if you want to implement this, or if you want to follow the suggestions in the results section, then that would be relatively easy to do. So I'm going to abort this here and just show you the solutions of this thing. So open the solutions database. I'm going to add the solution. I want to have the solution itself. Draw. Okay. Now let me also just extend this in the third direction. Transform, elevate, draw. Okay. So this is how this looks on the coarsest mesh. Of course, there's not very much to see. The mesh is just too coarse. Let me get rid of all of that stuff around it. Okay, apply. Dismiss. And then I also want to show you the mesh just to show why it is looking so ragged. For that I need to say operator attributes, elevate, and I want to elevate by the solution. Okay, apply, dismiss, draw. Okay, so this is the mesh, and you see why the solution looks so ragged. It just cannot resolve the boundary values, but if I refine my mesh further and further, it comes closer and closer. Okay, so this is how the solution looks like for this program. And like I say, the main drawback of the program is that we would have to have some sort of way of defining the step lengths in a better way, but then we would converge very rapidly towards the solution. So with this, I would close this. In the next lecture, I'm going to show you how we can replace the Newton solver by something that just solves the same problem by a fixed point approach, which in this case is also not particularly fast, but compared to Newton's method for a fixed point iteration, there's nothing you can do about it. For a Newton method, at least you can play with the step length, and that would make your life a little bit easier and would make the whole thing converge faster. So that's the main piece that is missing from step 15. So with this, I would say we'll leave Newton's method behind and move on to other ways of solving the minimal surface equation.